All right, here's 5.4, and we will go through the lesson. So our expectation is to write down the notes so that when we can continue or review afterwards. Okay, so 5.4, talking about mutually exclusive events. So if you're a group that has the whole booklet, you don't have to worry about this. But if you are if you just have part of this booklet, then you will need to transition at some point during this lesson to the new booklet. Okay. So here we have I'm gonna have my highlighters ready, and there's some instances where you highlight various points to be made. Okay, so we're going to talk about mutually exclusive events and how is that related to probability. Okay, so remember probability, we always have a fraction. We try to come up with a fraction, even though it can also be stated as a percentage or a decimal. But you also want to always keep in mind that you can still write a probability can always be converted to odds. Okay, always keep that in mind, and I will actually throw that in from time to time so we don't forget about it. So two events are mutually exclusive if they don't share any common elements. I think you remember that on a Venn diagram, there's no overlap, right? There's no intersection, or if there is an intersection on the graph on a Venn diagram, it would be empty. Okay, there's nothing in there. So recall from chapter 4, we had to split questions into cases when two or more conditions have an overlap, right? So those would actually be inclusive when they do have things in common. Then we have to kind of split it up and consider that overlap. Also recall from chapter 3, that was the set, right? Set notation, right? That first of all, let's talk about pi. So I actually, in hindsight, I would like this to be gone here. Let's just consider the principle of inclusion and exclusion that we learned about in chapter 3, right? This was the formula, like the union or A or B, right? Or people have at least one of the sets, right, is found by adding A, adding B, subtracting the intersection. There's a variant of this formula, but I always like to stick with that one. If the events are mutually exclusive, right? If we have mutually exclusive events that we're talking about, then that intersection there is null, right? There's nothing in there. So this really translates to just this. Okay, so why is this important to make that distinction? Well, if in fact, right, there is no intersection, then we just don't need to worry about, right, that third part on the equation. We can just go ahead and add things up. But if there is an intersection, which in this section, we will actually, oddly enough, focus on the overlaps, like instances where we're considering two events and there is some double counting that will happen if you don't consider the overlaps. We will actually tackle it. So this is obviously mutually exclusive here. So in this example, if you look at this Venn diagram here, notice that there are no outliers. Here, the union of A and B would simply be 30 plus 40, okay, which is equal to 70. Since there are no outliers, it actually matches the universal set. So no surprises there. Similarly, when we're dealing with probability involving inclusive events, then so when it's probability now, notice that the notation has changed, right? From number of elements to now probability. So this is a probability, everything is probability, but it still follows pi, right? If you want to, how do we turn this into this? you would essentially divide both of these sides, everything, by the universal set. And then basically it turns this into a probability, this into a probability, and so forth, right? So that's what makes these two different, is that this would have the universal set under every single term in this equation, okay? So here's your new formula, and it stems straight from principle of inclusion and exclusion that we learned in chapter 3. If events are mutually exclusive, meaning that conditions or restrictions do not affect each other, it's just this formula which omits that overlap, right? Since probability of A and B occurring is 0, okay? So here we have it. Using the Venn diagram to the right, answer the following. So one thing that I wanted to keep open, but I'm going to give you that the universal set in this case is 75. Okay, so it's indicating to us that there is an overlap. We just have to fill in this Venn diagram. So we're supposed to find a number of elements that are at the intersection of A and B, right? Elements that are in A and B. So this chunk right here is N of A and B. Okay, that's what we're trying to find. So I'm going to use the principle of inclusion and exclusion, which goes all the way up to, right, N of A union B is NA plus NB minus NA at B, okay? Intersect B. So really, this part right here, how do we get that? We have to take 75, which is the universal, and subtract any outliers that may be present. N of A, number of elements in A is 20, number of elements in B is 40, minus, I'm going to call this X, right? So this is 55 is equal to 60 minus X, take away 60 on both sides. That gives us -5 is equal to -x, which if you divide both by -1, x is equal to 5, right? So we actually found that n of A add to B is actually equal to 5, okay? If you want to answer it properly. So we can go ahead and fill in the Venn diagram now. Should not be a difficult task, right? This would be 15, this would be 35. We subtract from the set, and there we have it. And so the number of elements in the universal, we already have that, that's 75. No problems there. So why is N of U very important in chapter 5? Well, we need it to come up with probabilities, okay? So let's come up, so this is going to be very similar to chapter 3, except for note that we're dealing with probabilities, okay? So probability of only A not B happening, right? So what I can tell you right off the bat is you're going to have to put the universal underneath. That's all of possible outcomes, okay? And so we're going to go A not B. A not B is 15, right? If you reduce that, that's 1 over 5, which is 0.20, which is 20%, okay? So comma 20%, so we've got it all there. B not A, probability of B not A, hey, that probability tells me that I need to divide it by 75 or have it over 75. B not A is 35, okay? 5 goes into both of them, and that'd be 7 over 15, okay? Which is 4667 or 46.67%. Okay, there you have your 3 ways of answering. It's a good habit, and sometimes you can see connections between one and the other. What's the probability of A union B? So there's a couple of ways you could do this. You can add these three values, or you can just go 75 minus 20. Okay, I'm going to go ahead and do that over 75. So that's 55 over 75. Zoom out a bit here, it looks like over 75. Okay, which turns out to be 11 over 15, right, as a fraction, which would be 0.7333, which is 73.33%. Still have to zoom out. Sorry, guys. There we go. And so you've got that, and then a naught. Let's throw in a naught. Probability of A or B naught. How would you do that? Well, there's a couple ways to do that. It's almost like probability of it not happening. So you can just look at this fraction, right? If 11 out of 15 times it does happen, then it stands to reason that 4 over 15 it will not, right? Which is 0.2667 or 26.67%. And if you think about it, you add up the fractions, you get 15 out of 15, that's 1. You add up the decimals, that would give you 1. You add up the percentages, that would give you 100%, right? So there's the, right, something happening, something not happening should add up to the complement, we call that, right, should add up to 100% or 1 when it comes to probabilities. How about F? What are the odds of B, let's say? Odds of B. How would you do that? Odds of whatever B stands for. Of it raining, of, you know, somebody missing classes, of it landing on tails or whatever. But in this case, we don't know what it stands for. But what we do know, odds of B, what we need to do there is we have to say, well, it's B compared to not B. So that would be 40 to, on the other side, I would just take my universal and put, take the 40 away from it, right? Because that is what is not. So 40 to 35. If you divide them both by 5, you get 8 to 7, right? That would be even better if you can do that. So there we have it. This would be the odds, and we can go odds against B. That'd be 7 to 8, stuff like that. So you got to just watch out how you do that. Okay, come with me to the next page, 23. Let's consider a work problem here with percentages. Okay, there are a couple of questions. I will do at least one right now. Okay, so a car company reports that for a particular model, 43% of cars have heated seats, 36 have sunroofs, 49% have neither. Right? So I don't know if you realize, right, but there's a set, neither, right? Neither, you should recognize those are your outliers in this case. They don't belong to either set. Are these events mutually exclusive? So when it's asked of you to check whether or not events are mutually exclusive, you want to make sure that the sets plus outliers, right, equal the universal. That's what you want to do. Okay. In this case, the universal is 100%, right? In this case, I will say, in this case, NU is 100%, right? Because we're dealing with percentages. So we're going to check. So this is our check here. We're going to go, we're going to add the 43% that represent heated seats, cars involving heated seats, cars involving a sunroof. And by the way, we can tell that there's a chance that, of course, there's a way that a car could have both, right? So it's not out of the question here, right? So I'm going to add the heated seats, the sunroof, and I'm going to add the outliers. And if I do that, I get 128%, right? So this is 28% above, right, the universal. Okay, something like that. This indicates that 28% of cars have been double counted. In percentages, it makes it easy, right? Because they don't need to give us the universal. We already know. Okay. So since therefore, we can just conclude, therefore, these are not mutually exclusive events. Okay. If they were mutually exclusive, then if you added the two sets and the outliers, you should get 100%. We are doing that and we get more than 100%, which means that there is an overlap between these two. There has to be. So it says find the probability of a car having both. Just a little giveaway, it's going to be 28%, but this is how you would do it, showing proper work. So we will draw a Venn diagram, okay? So I'm going to go heated seats, sunroof. Heated is 43%, sunroof is, you've got 36% there. Make sure you have a box around it. You've got your 49% here, and your universal is 100%. Okay, so we've got that, and so we can use the pi, right? We can use pi using percentages. So we're not going to use that same formula, but we're going to use percentages, which stand for probability, right? There's a 43% chance that the car has heated seats, 36% chance it has sunroof, and 49% that it doesn't have either one of those. So we're going to go 100 minus 49, right? That will give us the combined, right? We take the 49 away from the universal, and that's 43 plus 36, and we're going to call this section here x, right? Minus x, so that gives you 51 is equal to 79 minus x. Take away 79 on both sides, and so that leaves us with negative x, and on this side negative 28, which we already predicted was going to happen. Divide both sides by negative 1, and so x is equal to 28%, right? 20% of cars have both. Okay, so not mutually exclusive because it didn't add up to the universal, which in this case was 100%. What if it asked you the probability of sunroof but not heated seats? Okay, what if it asks you that? Well, you would just go it's basically saying only sunroof. So you got to do a little bit of work here. So I'm going to use my pen, and that's 28%. Okay, sorry, 28% there, and that makes this would be here. This would be 36 minus 28, which is 8%, and then you go 43% minus 28 as well there, and that's 15. So you just fill that in just in case. So only sunroof would be 8%, right? 8%, which would be 8 over 100, which would be 4/50. You can still split that in half, 2/25. Okay. That's that. What if it asked you for the odds? Let's add a D here. Odds of a car having only heated seats. You got to be able to work that out, right? You got to. Okay. Odds of a car only having heated seats. So odds of what? Only heated seats. So you want heated seats only, right? So basically heated seats, not sunroof. And on this side, you're going to have the not, right? You're going to have the not. So heated seats only is would be 15%, which is, hey, let's do this, 0.15. That's 15%. And on the other side, you can have the other, whatever's remaining, which is really 1 minus 0.15, right? So 15% here, so the other side must be not. So that's 0.15, sorry, not equals, sorry, that should be a colon there, 0.85. Multiply both of them by 100, okay? You multiply both sides by 100 to get rid of the decimals. So you're like, why didn't you just keep it the same way? Well, there it is, okay? So we can actually go ahead and do that. So you can divide both of them by 5, right? This would be 3, and this would be 17. Yeah. So 3 to 17 would be the odds of only having heated seats. So be comfortable with that. How would you do probability from those odds? Right? How about this? Turn to probability. How would you turn this to a probability? So probability of heated seats only. Just using this. Don't use the Venn diagram, just this. You'd be 3, right, over, you add that up, 3 plus 17, which is 3/20. Okay. So you've got that. By the way, 3/20 is, if you turn that into a decimal, or decimal will be 0.15 or 15%, which is all confirmed by our Venn diagram. Okay, I just want to make sure you always understand that there's a way to get from one to the other, just like that. Okay. I will skip this one. I will probably just tell you that, maybe this, I'll give you the answer to that. That's 78%. Okay, to that one. Find the probability for B, that is 54%. That way you can give that a try. It's basically the same steps that we just took here on page 23. So keep going. 25. And I think at this point, I'm going to ask you to transition to the second part of the book, because this part is, this is overlapping there. It's part of the other booklet. If you don't know what I'm talking about, just keep going with your notes as usual. So, but as for me, I'm going to right now just scratch this whole thing, and I'll say C part 2. C part 2 of the booklet. So that second part of the booklet has a cover that looks exactly the same as this one that you got the probability. Just put chapter 5, right? Probability part 2. This is part 2, and I don't know if you want to put on this one part 1. and then you will be able to follow a little better with this example here, because I've introduced some charts there. Okay. So page 25, if you have highlighters ready, this one will be a very good candidate for that. So let's consider this. We've got two six-sided dice. So when you're doing two dice, it's a good idea to set out an outcome table with all the possible outcomes. And sometimes it will ask you, the probability of rolling doubles, for example. You can tell that the doubles are right down here, this diagonal line. So there's 6 out of 36, right? And this could change if it's like a six-sided and a five-sided, right? Then you do this. Or if it's a four by five, right? Like a four-sided and a five-sided, it changes a little bit. The outcomes change, and you just have to kind of adapt accordingly. So this question reads, two six-sided dice are rolled together. What's the probability that the sum is greater than 8 or, right, a multiple, and or is a big giveaway in this unit, everywhere really in math, of adding, or a multiple of 5, right? So you want the sum to be greater than 8. That's event 1, and or a multiple of 5. That's event 2. Multiple of 5. I'll just write that there. It's easier to see there. State the odds as well. Okay, so we're going to do that as part of it. So let's go ahead and try this. So sum greater than 8. So you will become very familiar with an outcome table like this involving dice, but this would be a sum of 2, right? Sum of 3, 4, 5, 6, 7. So you don't quite get there. Let's jump here. Oh, there's 8, right? 6 and 2 is 8, but you want the sum greater than 8. So let's jump down. 3 and 6 is 9. This is 8, see? This is 5 and 3 is 8. This is 9. So if you look carefully, 6, 2 is 8, 5 and 3 is 8, 4 and 4 is 8, 5 and 3 is 8, 6 and 2 is 8. So this is your 8 line. We want greater than 8, so we're going to actually do this. These numbers, right here, these combinations, right, give us a sum that's greater than 8. Not greater than or equal to, we want greater than. So just check, right? This is all adding up to 9 here, and then it's adding up to 10, and then it's adding up to 11 and 12, right? So those are the outcomes that give us that event, that take care of that, right? Then the second event is having multiples of 5, or that second, you can almost look at it as two different conditions or restrictions, right? Or two different sets, okay? So there we have, right? I will do this, multiples of 5. I will highlight that there. You want the sum to be a multiple of 5. So if you think about it, getting a 5, right? If you get a sum of 5, that would definitely do it, because think of it, multiples of 5, you want a sum to be either 5 or 10, or the next one will be 15, but that's already past the ways, the opportunities, right? That's past, because the highest sum you can ever get is 12, right? So you want a sum of 5 or 10 to consider for this. So sum of 5 is right here. If you consider this angle, that is a sum of 5. So all these add up to 5. And then our next one would be a sum of 10. If you go down here, 6 and 4 is 10, 5 and 5 is 10, 4 and 6 is 10. So these three are going to add up to 10. And you notice that that's your overlap right there. Okay? You've got, these give you a sum greater than 8. These two combinations here, the highlighted ones, give you a sum that is a multiple of 5. Okay? So if you allow me, let's do a Venn diagram real quick just for this one. I don't want to do it for all of them. You just follow along. So this would be multiple of 5, and this would be a sum greater than 8, let's say. Okay, that's our setup there. And so let's take care of the ones that overlap. In fact, I'm gonna do this. These I'm gonna go orange yet around it because those are the overlap, right? That would represent this region here in our Venn diagram. And so that would be 4, 6. So 4, 6. Let's spare ourselves that. Maybe 5, 5, 6, 4. In my notes, it's usually a good idea, but I don't want to spend too much time on this. But yeah, so this is the one they have in common. And then if you go multiple of 5, that'd be 1, 4, 2, 3, 3, 2, 4, 1. So we're actually writing down the combinations here. We won't do this one again because it's already part of it. That's the overlap. So let's go sum greater than 8. So that'd be 3, 6, 4, 5, 5, 4, 6, 3, right? I won't do these, but I will do this one. 5, 6, 5, 6, 6, 5, and 6, 6. Okay. So if you think about it, let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 in that set, sum greater than 8. A multiple of 5, that set is 1, 2, 3, 4, 5, 6, 7, right? And you can confirm 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10, so it all adds up. What's my universal? Well, remember universal is just 6 times 6, like your two events, the total number of outcomes possible. Okay, so that is 36. I'm going to put it down there. And yes, technically you should list, if you want to do a proper Venn diagram, you would have to list all of the sets that do not pertain to either one of them out here. I won't do that. I will just say this. Out of the 36, right, we're going to subtract 7. So that's these 7 here. And then we're going to subtract 1, 2, 3, 4, 5, 6, 7, another 7. And then so that's 36 minus 14, right? That's 22 22 combinations that would not belong to either one of those sets, okay? So this is our Venn diagram. Now let's actually go and answer the question, okay? So that would be probability of a sum that's a multiple of 5 or a multiple or a sum greater than 8. You're actually asking for the union, right? If it's asking it like that, that would also be correct. So we know that it's always going to be out of 36, so we can actually write it like that. So we can go 7, right? 7 for the first set plus 10 for the second set, and then we're going to subtract the overlap, which is 3. Okay. So in that case, we have the 10 minus 3 is 7, right? So 7 plus 7 is 14. So it'll be 14 over 36. Split that both in half. That's 2 over 18, which is 1 over 9. Okay. 1 over 9 is the probability. So that's 0.1111 or 11.11% that we will consider there. Okay, one more here, ready? We're gonna, now we want a sum that's a multiple of 4, right? Multiple of 4, or a sum that's greater than 6. We can also go G6, that's fine. Okay, so multiple of 4 means that the sum has to be equal to 4 8, and we can actually also include 12. That's the greatest sum you can ever get, right? And so let's find the greater than 6 first. Greater than 6. So we get 5 and 2 is 7, right? So this is my 7 line. So that's perfect. So I'm just going to go ahead and do this. So everything to the right of that diagonal line, this would all be greater than 6. Right? Sum is greater than 6. And then we will highlight the multiple of 4. A sum that's a multiple of 4. So multiple of 4 would be your 4s. So that would be this. These combinations here add up to 4. And then your 8, which is here, right? 4 and 4, 3 and 5, 26, like that. And then we have our 6 and 6 right down here. Okay. So no Venn diagram in this case, but I will circle these because we need to make sure we don't count them twice. Okay. So probability multiple of 4 or a sum that's greater than 6. Well, let's do one at a time. Multiple of 4. Let's just count all the highlighted ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Plus, let's count all the numbers, the combinations that give us a sum greater than 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Okay, so it's 21 minus, we're going to take away the overlap. So 1, 2, 3, 4, 5 minus the 1. Okay, all of that, remember we're talking probability, all of that in this case over 36. Okay. So here we have it. We're going to go and add that up. So this would be 30 minus 6. That's 24 over 36. Right? Oh, you can simplify that for sure. 3 goes in there 8 times. 3 goes in there 13 times. Sorry, 12 times. We can keep going. 2 goes in there. 4 goes in there 2 times. 4 goes in there 3 times, so it's 2/3, right? Which makes sense. We could have divided both of them by 12 right off the bat and arrived to the same. So that's 0.6667 or 66.67%. And so there you have it. That's how you would do a question like this. So you don't have to do a Venn diagram. That was just to show you. Let's still answer the odds. The odds for, right? Odds for, I'm going to go arrow. That would be in this case, let's use our simplified fraction, right? 1 to 9 minus 1, right? So it's 1 to 8 against would simply be 8 to 1. So out of 9 times, 1 time you could get one of those conditions or meet one of it, but 8 times you wouldn't. Okay, so not a very good chance. Over here, you have a greater chance, right? You have a 66% chance of that happening. So odds for or of would be 2 to 3 minus 2. So it'd be 2 to 1. And against would be 1 to 2, right? Just flip that. There's that. What I want you to work on, and if you keep flipping here, there are more to try. I put more than what I needed. I'm just gonna maybe answer this one here. What's the probability of drawing a queen, a red queen, or a face card? Okay, a red queen or a face card. So you gotta watch out there. I will show you how I would do it. So right there, you're like, wait a minute, is there an overlap perhaps? Right? And so for example, if you go red queen, number of red queens, and that would be 2, right? 2 queens, there are 4 queens, 2 of them are red. The number of elements that are face cards, or number of cards that would go under the face cards, is 12. Okay, so we know that if you have your 12 face cards, right, that these 2 red queens would be part of it, right? It would be part of the face card category. So you technically don't have to add it, like you would be adding it twice if you add both sets up. So, and you know that, so the number of elements that would be considered, that where you consider both, right, that they both have in common, like if you drew the intersection between these 2 sets, right, it actually ends up being a subset, right? And note, RQ, right, is a subset of F, right? So because all elements in RQ and red queen are part of F, so they're subsets. So if you want to visualize this, if this would be your face cards, right, there's 12. You've got 2 black queens, and right, this would be 2, and red queens would be 2 as well, but they're nonetheless inside the face card category. So if you want the intersection, well, this whole thing is inside that. So there's actually 2, right, that they both have in common. So to figure out the probability of red queen or a face card, okay, or the union of those 2 sets, we'd have to go 12, right, or red queen is actually 2 plus 12, and then we'd have to subtract the intersection. And all of that is over, how many cards are there? 52, we're talking probability here. So that's actually 12 out of 52. 12 to 52, which reduces, right? This splits in half to 6 out of 26. You can split that in half further, 3 over 13. Okay, so that would be your fraction. And then you have, if you want odds, state the odds. And we're assuming it's of. We take the reduced fraction, it's 3 to 13 minus 3. So it's 3 to 10. Okay. There you have it. All right, so here's this is actually straight from the textbook, but I thought I'd add it here. It summarizes the key ideas of this section. You can look it over. So what I want you to work on is on pages 28 to 29, right? 28 to 20, page 28 to 29, and I will post the answer to you. It will show up 28 to 29. Okay, and I expect you to have this all written down and work through for the next day. All right. Have a good one.